Near the beginning of this unit, we learned about a discovery by Hans Christian Ørsted almost 200 years ago. 1819, he discovered that electricity will generate magnetism. It was simple as that. You had a moving charged particle, it would always generate a magnetic field. Well, let's fast forward 12 years. Let's talk about what we call the generator effect or electromagnetic induction. Same thing. A discovery that was made in 1831 by two guys independently of one another. A guy named Michael Faraday, who was a British guy, and a guy named Joseph Henry, who was an American, both independently in two different continents, around the same time discovered that, well, if electricity generates magnetism, magnetism will also generate electricity. But there's a little asterisk beside this one, because while electricity will always generate magnetism no matter what the orientation is, the direction is, and so on, as long as you have an electric current, you will always have a circular magnetic field produced. You will not always get electricity produced by magnetism. You have to have certain conditions met. One, you have to have two things. You have to have a conductor and a magnetic field. If you don't have a conductor and a magnetic field, then you're not going to generate electricity from magnetism. You got to have a conductor, which is basically a wire, right? A wire, usually at least, and a magnetic field, which is usually magnets. Now, it's not enough to just have a wire and a magnetic field. Okay, if you've got a magnetic field right here and a wire sitting right here, nothing happens. You've got to do something to the wire and or the magnetic field to cause an electric current to be generated by magnetism. Here's what you got to do. One of the following. You can move the conductor. If you have a magnetic field and a wire sitting right here and you move the wire, then you'll generate an electric current in that wire. What do you think the second thing would be? Okay, I've given you the first one. A little bit of logic might tell you what the second one is. Yep. Yeah, move the magnetic field. Okay, if you got magnets that's causing the magnetic field, move the magnets. It doesn't really matter which one you move. Okay, moving one is exactly the same thing as moving the other. It's all relative, right? You guys now know how just about every bit of electricity that comes to our houses is generated? By the generator effect or by electromagnetic induction. In Ontario, they use a lot of hydroelectric power. Okay, in Ontario, they dam rivers, and these rivers become big lakes, and they go really, really high. They got a lot of gravitational potential energy. Water up high with all that potential energy goes down through this penstock, turns a turbine, and generates electricity. That turbine, essentially, this is a little bit of a simplification, but it boils down to some strong magnets, and as the water comes down and turns that turbine, it moves a wire. It moves loops of wire through a magnetic field. Okay, so that's condition number one. Move a conductor through a magnetic field, generate an electric current. Okay, in Alberta, we generate most of our electricity from burning coal. We talk about all this clean energy and wind power and so on, but still the vast majority of our energy is generated by burning coal. When you burn coal, it doesn't generate electricity directly. What it does is generate heat. And that heat boils water, turns the water into steam. Steam rises and turns a turbine, moves a wire through a really strong magnetic field and generates electricity, just like the hydroelectric dam did, right? Nuclear power. They have nuclear power in Ontario again, and in New Brunswick, and in all kinds of the states in the US, and in lots of countries in the world. Nuclear power doesn't generate electricity directly. Nuclear power generates heat. What does heat do? Boils water, turns water into steam. Steam rises and turns a turbine, which consists of a bunch of wire that's moving through a magnetic field and generates electricity. So just about all the electricity that we have in our houses today is based on this principle of the generator effect or electromagnetic induction, discovered 12 years after Ørsted's discovery. What would be the one notable exception of electricity generated in a way other than the generator effect? Solar power, exactly. Okay, solar power is a completely different principle. That's not a widespread production method for electricity, at least not yet, at least. The third way that we can actually generate electricity from magnetism is not by moving one of them, but rather by changing the magnitude of the magnetic field strength. So a weaker field, stronger field, okay, change the strength of the magnetic field. Now, we don't see that one that often. Okay, in Physics 30, we almost always deal with either moving the wire or moving the magnetic field. But on your assignment that's due tomorrow, this one actually does appear. Okay, that third principle does appear. It's called the electromagnetic induction. When you generate an electric current from a magnetic field by moving the wire, by moving the magnet, or by changing the strength of the magnetic field. All right, let's take a look at the last topic that we do this unit called the Lenz's law. This is a combination of a couple of things that we've already learned. The first thing is what we just learned a few minutes ago, and that is this idea of electromagnetic induction. If, as in the demonstration that we just did, we have a conductor, which in the demonstration was the copper tube, and a magnetic field, which was the magnet that Dylan was dropping, that Jessica was dropping. If we have a conductor and a magnetic field, and we move one of them, doesn't matter which one we move the magnetic field. We could have moved the conductor just as easily, and we would have the same effect. We move one of them, then we're going to generate an electric current. It's a small electric current, but it is an electric current generated in that copper tube. Small enough that I'm not going to feel it or get injured by it, but it is an electric current. Okay, that's Faraday. That's what we just learned about, right? Now, Oersted said, think back to near the beginning of this unit, Oersted said that an electric current will generate a magnetic field. Well, we've got an electric current now, right? We made the electric current from a magnetic field, but we've got one. That electric current will generate a magnetic field. Hey, again, Oersted, what Oersted taught us way back near the beginning of this unit. So what we've got here, just quickly summarize it before we go to the big conclusion here. We've got a magnetic field generating an electric current. Now, the electric current that's been produced in turn generates another magnetic field. So we've got two magnetic fields. The one that we dropped, the one that we moved originally, the magnet, and the one that was produced by the electric current that was produced by the original magnetic field. We got two of them. Those two magnetic fields, and here's what separates Lenz from Oersted and Faraday, right? So far, nothing new. Okay, this is just Oersted and Faraday. What separates Lenz from Oersted and Faraday is that those two magnetic fields will always act together to oppose the motion. If it's the magnet that's moving, the motion of the magnet will be opposed. If it's the conductor that's moving, the motion of the conductor will always be opposed. Now, we know there's got to be a force. If you get two magnetic fields, there's got to be a force. Why does it have to be an opposing force? Why can't it be a helping force, a force that helps it down even further? Well, let's think back to the demonstration. If I dropped a magnet through that copper tube and it accelerated not at 9.81, but at 15, then it ends up with more kinetic energy afterwards than it started with potential energy at the beginning. What have we just done? We just created energy from nothing. We just violated the law of conservation of energy. We know there has to be a force, and it can't be a force that helps it along. Otherwise, you'd be creating energy from nothing. So therefore, the only other option is that it's got to be an opposing force. Magnetic field causes current. Current causes second magnetic field. Those two magnetic fields act to oppose the motion. Otherwise, it would violate the law of conservation of energy. I want to draw a couple pictures here to apply this, okay? Let's say we've got a magnet right here with a south pole and a north pole. We've got a coil of wire right here. Do you see what I'm doing with this coil of wire? The front and the back of the coil. You see that? The dotted is kind of in behind there. We're going to attach this time a light bulb to it, not a battery. What happens to that light bulb right now? Right now, you got a magnet sitting there, you got a coil of wire just sitting there. What happens to the light bulb? Nothing. Nothing. If we move this, here, I'm going to copy this because I'm going to use the same picture again in a second here. If we move this magnet nearby this conductor, though, then we've got electromagnetic induction taking place, a generator effect. We've got a magnetic field and a conductor, and we're moving one of them. That generates a current. Now, which way does the current go? I don't know right now, but I know there's a current produced in this, and the light bulb will turn on. Let's figure out which way the current will go using Lenz's law. By Lenz's law, as I push this magnet towards the coil, there is a current produced, and that current will produce a magnetic field that will act with this to oppose the motion. What's the polarity of this coil become after the current's produced if it's going to oppose the motion? What end is this, north or south? It's got to be north, right? If I'm pushing this towards it, the only way to oppose that motion is to have a repulsive force. That makes sense? It becomes a magnet because there's a current produced by the moving magnet. That second magnetic field acts along with the first one to oppose the motion of the original magnet. Now we can figure out which way the current goes now. We can take that piece of paper like we did earlier on in the unit, wrap it around. Say my thumb goes from south to north inside. That's the direction of the magnetic field. Okay, so my thumb goes this way. My fingers would point down in the front. So the electric current would go down in the front like this, up in the back, or it would end up going counterclockwise. We were able to determine A, the polarity of this induced magnet, and B, the direction of the current that caused this induced magnet just by using Lenz's law. Now I want to change this ever so slightly. We'll keep the same setup here, except this time we're going to move the magnet to the left. We still have a magnetic field moving relative to a conductor, right? We still get a current produced. Which way is the current? I don't know. What's the polarity of this new electromagnet become? What end is this, north or south? This would be south this time. I heard a couple of people say that. This would be north. Why? Lenz's law never said we get a repulsive force. Lenz's law says the force always opposes the motion. If I'm pushing this magnet closer to it, what's going to oppose the motion? A repulsive force. If I'm pulling this magnet away, what's going to oppose the motion? An attractive force. North and south. Does that make sense? Now, how do we figure out the direction of the current there? Well, we'd say the magnetic field inside goes from south to north. We'd say our thumb goes to the left. Our fingers would go up in the front. Or the electric current would be up like this, which is clockwise. Either way, the light bulb turns on. But we have an electric current in one direction causing one polarity and the other direction causing the other polarity. Devin? Yeah, absolutely. Absolutely can. Darwin says you can buy flashlights based on this principle. I have one at home, actually. It's funny because I never actually use it. Mine's actually a crank one. You shake? Okay. So, yeah, so whether you crank it or whether you shake it doesn't really matter. What it boils down to is that you're essentially either moving wire relative to a magnet and generating the electric current in it, or if you shake it, you're probably moving the magnet inside the coil wire, generating the electric current.